All right, so a couple of things we already know. We already know that if I have a graph of velocity versus time for a constant acceleration, then that graph is a straight line whose intercept is v0, the initial velocity, and whose slope is the acceleration. And the equation for that line is v equals v0 plus at. Now from that, we should be able to get an equation for the position as a function of time. A couple of things here. If I had a constant position as a function of time, if I had a constant velocity, then the displacement would simply be the velocity times the change in time. Well, that's just the area underneath the curve. So one way that I can find the displacement is by finding the area underneath the velocity versus time curve. And it turns out that holds true even when I'm considering a changing velocity. It would even work in the case of a curved velocity, but here we're doing it in the case of a constant velocity. Essentially, that's why an integral is the area underneath the curve. We're undoing the derivative. So all I need to do here is figure out All I need to do here is figure out the area underneath this curve. The easiest way to do that is to break it into two parts and say, all right, this velocity at the end I've got here, it's v0 plus at. This part here is v0. This part here must therefore be at. And now I simply have to find the area of the rectangle and the area of the triangle. Well, the area of a rectangle is easy. That's just base times height, or v0 times t. The area of the triangle is not much harder. That is simply 1/2 the base, that's the time, times the height, at. So in other words, my entire displacement, delta x, is equal to 1/2, let me change that. My entire displacement is equal to v0 t plus 1/2 a t squared. Now there's another way I could have looked at that we'll come back to in a minute. So what this tells me is that I've got an equation that says v is equal to v0 plus at. So that's an equation for my velocity. And I have an equation for my position that says delta x, which is x minus x0, is equal to v0 t plus 1/2 a t squared. Or x is equal to x0 plus v0 t plus 1/2 a t squared. So these are my main two equations that I will use throughout our discussion of kinematics. Now there are other ones. I could take this top one, solve it for the acceleration, and plug it into the bottom one, therefore eliminating acceleration from my variables. It turns out my answer in that case is that delta x is equal to 1/2 v initial plus v final times the time. We don't include that as one of our main ones because it just gets a little confusing. For one thing, this equation only works if it's a constant acceleration, even though acceleration is not in that formula at all. My two main equations also only work when it's a constant acceleration. You must be very careful on problems because sometimes problems begin with someone throwing an object or catching an object, and during the throw and the catch, the acceleration is not constant. These equations only apply during the period when the acceleration is constant. The other way you can get this formula here is if we consider this shape here. If I turn it on its side, it's a trapezoid. Two parallel sides and two non-parallel sides. Well, the area of a trapezoid is the average of the two parallel sides, so that would be 1/2 the initial velocity plus the final velocity, and then multiply that times the distance between them, which is just the time. There's one other major equation that we will get later on, and there's other ones. You could solve this to eliminate v0 from this equation. All sorts of different ways you can do it. But these two are the main principal ones that we use when solving kinematics problems.